Hey everybody, welcome back to Environmental Organic Chemistry with Dr. Lisa. We're going to work on homework number 3 today. And homework number 3 should look kind of like homework number 2, so hopefully if you've mastered homework number 2, homework number 3 won't look quite so intimidating. You're asked to do basically the same things, except now we're thinking about the aqueous solubility of your chemical. So the first thing to do is look up the aqueous solubility of your chemical at 25 degrees C. And report it in units of molar as well as milligrams per liter, and ask the question, is your chemical a solid, liquid, or a gas at this temperature? So obviously we're going to need to also look up the melting point and perhaps even the boiling point. So I've started to put together a little template for this, and the chemical I'm going to do today is naphthalene. And again, if you have EpiSuite, that's great. If you've got a PC, you can run EpiSuite. If you don't, there are some other places you could go to look up the solubility of something like naphthalene. Naphthalene's a pretty common chemical, so I went over here to the NIST web book and I can look up some stuff here, but I don't think it has aqueous solubility here. You could, of course, also go to our friend Wikipedia and look up naphthalene, if you can spell it. And it has some useful information here, and it does have some information on solubility in water. Here it is at 25 degrees C, 31.6 milligrams per liter. So we could use that as our value. Go back here. So this is the solubility. Let's see, CSAT. And we've looked it up again at milligrams per liter. 31.6. There we go. And I already looked up the molecular weight of this chemical. It's 128 grams per mole. So if I want to convert this CSAT-W into moles per liter, which is one of the first questions you're being asked, I need to divide this by grams per mole, right? So that, and that's in milligrams, right? So to convert that to grams, I would divide it by 1,000 to get it in grams per mole. So here would be my solubility in grams per mole divided by my molecular weight. And so this would be my solubility in molar, or moles per liter units. Okay, so, and let's look up the melting point and the boiling point of my chemical. Again, the boiling point, 217 degrees Celsius, so that's not going to be a problem for us. But look, the melting point is 78 well, there's a couple different measurements here, right? 78.2, 80.2. Melting point, if you've ever measured it, is not so simple to measure. It seems like it ought to be easy, but it's not really. So let's just choose 80 degrees Celsius here. That's close enough. So 80 degrees Celsius. And now you can see why I've chosen naphthalene, because it has a melting point between 0 and 100 degrees Celsius. So we're going to have to think about that when we do our plot here. Delta H of fusion, I was able to find here on the NIST webbook. I looked up naphthalene, and here's my phase change data. And if I scroll down, delta H of vaporization's here, and delta H of sublimation, and somewhere here is delta H of fusion. And again, you can see a lot of different numbers, but clustering around 19 kilojoules per mole. So we'll use a value of 19 kilojoules per mole. And we'll get to the Seshnov constant in a minute. Okay, we also need to know HEW, that's that excess enthalpy of solubilization. And HEW is not easy to find. It's actually one of the hardest things to find. And so we have to kind of punt a little bit. So what I usually do is I go to our lecture notes here. Here is the table that has a bunch of different values of HEW here for a bunch of different chemicals. And I would look at this and say, okay, where does my chemical fall kind of in this thing? Now, for naphthalene, we actually have a value here, and this is saturated and dilute, and we're probably in dilute solution, so I would choose 12 kilojoules per mole. So before I forget, let me write that down. 12 kilojoules per mole. But for a lot of other chemicals, obviously, you're not going to be anywhere on this plot. And so then you want to look at this and say, okay, this is increasing by molecular weight here. So I want to kind of roughly ask, where does my chemical fall in this range of molecular weight? And if my chemical is down here, kind of in this region, I would probably say, my excess enthalpy of solubilization is pretty close to 0. Maybe, somewhere between 1 and maybe 10 kilojoules per mole at most would be a reasonable guess. But when I get up to here to these big hydrophobic molecules, these would include things like PCBs and dioxins and big hydrophobic molecules, then I probably want to choose a much higher number between 30 or even 60 kilojoules per mole for my HEW. But the important point to understand is that this is a guesstimate. We don't have a formula for it. We're just doing the best we can with what we've got, right? So that takes care of part 1. Look up the aqueous chemical of your chemical. We got it in milligrams per liter and converted it to molar units. We've determined that this is the solubility of the solid here. Sometimes you might have something else depending on whether your chemical is a liquid or a gas or something like that. But we have the solubility of the solid. And now we want to estimate or look up the excess enthalpy of solubilization. We did that. And now plot the solubility of your chemical in molar units as a function of temperature from 0 to 100 degrees C in terms of the natural log of CSAT versus 1 over T. And remember to account for the transition to a solid or gas if necessary. So here we are. I've already taken the liberty. This is copied from the previous homework. This is our temperature and our 1 over T. So now I want to calculate my ln C sat W. And we're going to use this equation. Remember, I could express this as ln C at temperature 1 minus ln C at temperature 2. And then I could move, ln C at temperature 2 minus ln C at temperature 1. And then I could move the ln C temperature 1 over here. So my equation would look like this. It would be HEW. I'm going to put some parentheses in here. So here's HEW. Again, multiply it by 1,000 so that we can match units. Divided by 8.314 joules per mole Kelvin. And actually, I'm going to take out this parentheses right here and put it over there. Okay, so that's the first term here, right? That's the first term. And then multiply that by, oops, not a 9, parentheses. 1 over T1, so that's the temperature, that's our reference temperature down here, so that's the 25 degrees C, minus 1 over T2, that's this one here, okay, and then add on to this ln of our solubility at 25 degrees C, which is right here in molar units. Okay, and then we just do all of our dollar signs. I use F4 as a quick way. L12, that's going to stay the same. L7 is going to move. G9 is going to stay the same. Okay, there we go. Bada bing, bada boom. Okay, now, so this is all fine because this is now the solubility of the solid. Actually, oh, sorry, I made a mistake. Hey, sorry, this is not the solubility of the solid. If I want to do the solubility of the solid, I have to add onto here delta H of fusion. Sorry. And that whole thing has to be multiplied by 1,000. So I'm going to need an extra set of parentheses here. There we go. So when I'm moving my arrow keys, see how I don't know if you can see it, but the little parentheses light up. It tells you which parentheses is matching with which other parentheses. And these are in red, right? Okay, so D12 also needs some dollar signs around it. There we go. Now this truly is the solubility of my solid, and as a check, if I take the EXP of this, I should get 0.00025, because that's what I had over here at 25 degrees C, so that's just a check to make sure that everything's okay. But I'm gonna move that over here, because this is going to be straight up CSAT W. Okay, so we can plot this. I'll plot it as a line. There we go. That's not what I wanted at all. That's not even close. Sorry. Insert. Here we go. Do it this way. So it's just a line, it's not points. Okay, there we go. So there's our solubility, and this is of the solid. Okay, so what we want to do is I'm going to write in here solid. And then if I go over here and I go to my chart design and add a legend, then see it's showing up now. And if I don't want it to take up so much space, I can make this a little bit bigger. There we go. Okay. And as long as I'm being psycho, I could go in here and I could change my units. Make this look a little bit nicer. 0.025. There we go. Oh, that's lovely. So nice. Okay, so here's the solubility of our solid. The problem is that we've taken our melting point to be 80 degrees Celsius, which is right here. So at this point, this number is correct, but these numbers are not, because now the solubility is changing. Okay, so let's now calculate the solubility of the liquid solubility. So actually, let's do it this way. Copy that, and instead of saying solid, this is now going to say liquid. Okay. Does that look good? That looks good. Okay. All right, so how would we do that? Okay. Let's think about this. Okay, at this point, the solid and the liquid have equal solubility, because that's right at the melting point. That's where these two lines that we're going to draw are going to intersect. So we could use this as our reference temperature now. 80 degrees C is our T1 here. So we could basically just replicate this same formula. Let's just copy it over here and copy it down. Except that it's all wrong now. Got to move our temperature over. Okay. Okay, so that gives us exactly the same numbers now, but what we're going to do now is alter this formula, okay? So now, first of all, we don't need delta H of fusion anymore because we're a liquid. So we'll get rid of that, okay? And then also our reference temperature is no longer going to be 25 degrees C, it's going to be 80 degrees C. And now, I think, oh, yep, then we got to move this over too. We'll move this over here. For the moment, it'll give us a weird divide by zero error, but we're going to copy that. Okay, now this should work, because now I have a number here. This is my aqueous solubility right at the melting point, right? And I think I've done everything else right with this formula, right? So I've got the delta, or the HEW times 1,000 divided by 8.314. Difference in the reciprocal temperatures, where this is now temperature 1 is now 80 degrees C, and this is temperature 2. And then here's my solubility at 80 degrees C. So now if I copy this down, double click, voila, and I could click on this and I could just make this a little bit whiter. Bada bing, bada boom, baby. Okay, so now, first of all, let's make this look a little bit nicer so it's a little bit easier for me to draw on this plot. So I'm going to have the max go to -5. There we go. Okay, so now this looks nicer. So remember, again, let's add some useful stuff to our plot here. Chart design, axis title, horizontal axis. This is now 1 over T in Kelvin. I can type. Not very well, but I can type. There we go, 1 over T in Kelvin. And then we want to add our other axis title, our vertical axis title. This is now solubility in molar units. Gonna make this a little nicer so you can see everything. Okay, so there's our solubility. That's not what I meant to do at all. I'm trying to move this. There we go. All right, so the blue is the solubility of the solid. It decreases faster with temperature because it's got a steeper slope because you've added delta H of fusion in here. And the yellow, excuse me, the orange is the solubility of the liquid. So this region right here, sorry, so you can see the 1 over T there. This region is cold, right, because it's 1 over T. So over here we're cold and over here we're hot. It's backwards, right? So over here it's cold, so this is the region where the compound is really truly a solid and the solubility is dropping off rapidly. The solubility, so this right here is the solubility of the hypothetical subcooled liquid. Hypothetical because this is all a brain experiment. None of this is happening in the real world. There are no naphthalene crystals here in my office as I'm recording this. It's all just a thought experiment. But this is the solubility of your hypothetical subcooled liquid. Here's the solubility of your actual solid. And then to be really correct, we shouldn't be plotting this, right? Should just make that go away. Should just stop here because we don't, I mean, we could think about the solubility of the hypothetical superheated solid. That would be extending this line out, but I don't want to confuse you. Over here is the solubility of the true liquid in the area, the region over which it is a liquid. Okay? Does that make any sense at all? Hopefully, maybe, a little bit. So that's what we were asked to do here. Plot the solubility of your chemical and account for the phase transition. Now we're going to plot the solubility of our chemical in in terms of CW sat versus T, no longer natural log of CW sat versus 1 over T, but just CW sat versus T. That's easy. We've already gone halfway to there. So this is now going to be, so these I've taken the EXP of our solubility of the solid, and in this region it truly is a solid, so this is all good. But then here I want to take the EXP of the solubility of the liquid. Boom. There we go. Bada bing, bada boom. Copy that down. And now I'm going to do it this way. I'm going to take these two and plot those. I'm going to plot them as points. Sorry, not this one. I'm going to plot them as points here for now. We can change that later. And then I just swoop this over here. There we go. Okay, so now you can see here's the solubility of the solid increasing pretty dramatically with temperature. Then it hits the melting point and it continues to increase, and you can't really see the curvature, but there is some curvature here. But the increase is more slow now, right? Because we are now in the liquid region, and so we're no longer having to melt the solid in order to dissolve it in water. Okay, so that's part number, let's see, that's part number 4. Now find or estimate the Sessionow constant of your chemical. The Sessionow constant is what describes how it's going to behave in salt water. So if you go to your lecture notes and scroll down a little bit, here, there's this table. This is a very, very helpful table. So this is salting constants for organic compounds in seawater, which, you know, we're environmental people. We deal with seawater. This other table here is for all the weird salts, like you know, potassium bromide. We don't need to deal with that. We live in the world where it's all seawater. Okay, so we look at this table. Now, again, one of the reasons I chose naphthalene is because there's a value for it right here, 0.28. But if your chemical is not listed here, you know, most of the chemicals in the world are not, you need to look at this table and ask yourself, okay, which of these are kind of similar to my compound? So, you know, here's PCBs. These are all PAHs, nonpolar. This one's got an alcohol group on it, so naphthol. It's a little bit different. These are nitrophenols, so they're quite polar. Aminotoluene, that's an aniline with a methyl group on it. So that's relatively polar. The aniline makes it polar. These here are more nonpolar. So you can see nonpolar chemicals around 0.25 or 3. More polar chemicals, a little lower. These are aldehydes, very, very high Sessionow constants. So just pick a number that seems reasonable. You know, you're not going to get the perfect number here, but we're just pick something that's reasonable. So my value is 0.28. So here's my Sessionow constant, 0.28. And we had this equation in the lecture notes, and it was written in the form of activity coefficients, which, you know, nobody likes that. But remember that the activity coefficient is just the inverse of the aqueous solubility with this correction factor that is the molar volume of water. So that's a constant. So that's not a problem. So we could rewrite this equation just like this. Okay, same equation. The only difference is because CSAT in molar units is the inverse of the activity coefficient. Because it's the inverse, we just need a negative sign here. And then all will be well. So the question was to calculate the solubility of your, so we found the Sessionow constant, now calculate the solubility of your chemical in seawater at 25 degrees C. And we know that the salt content of regular old seawater salt is 0.5 molar. That's just no, not milligrams per liter, molar. That's just a weird coincidence that it's pretty close to 0.5 molar. And this is an approximation, so it doesn't have to be perfect anyway. So here's our solubility in fresh water. So our solubility, which we'll call CSAT-W salt at 25 degrees C, is going to be this CSAT-W times 10 to the power of, parentheses, minus Ks times salt concentration. Close parentheses. Bada bing, bada boom. Solubility has gone down. Same temperature, but now the solubility is lower because we're in seawater. And in seawater, all of those water molecules are busy trying to solvate all the salts. All the sodium and chloride and all that other stuff is sort of tying up the water molecules so that they're not available to solvate your chemical. So the solubility of your chemical will go down. And just to illustrate the point, it has gone down by So this solubility is 72% of the solubility in the full fresh water. So it's gone down by close to 30%. So it's not a huge, it's not orders of magnitude, but it is a depression, 30% depression. And that's in full-on seawater. Of course, if you were in Raritan Bay, the molarity there might be 0.3. So the depression and the solubility of your chemical would be a little bit less because there's less salt. Anyway, that's a quick tutorial on how to do homework number 3. And let me know if you have questions.